In the last lecture, we talked about environmental impact factors of different PV technologies. The impact of a technology is closely related to the material choice and total material consumption. Today, we will discuss about specific materials used in PV, such as silver, silicon, copper, lead and other metals. 3 topics will be covered in today's lecture. Material use in silicon PV and material use in thin film PV. In both cases, the corresponding environmental impact will be addressed. Here we show a typical device structure of a passivating emitter and rear cell, or PERC for short. It represents the current mainstream industrial technology. More details about this technology can be found in textbooks, but also in our previous course. On the right hand side, we see a simplified structure of a crystalline silicon PV module. It includes glass, an aluminum frame, polymers such as ethylene vinyl acetate or EVA for short, a backsheet, a silicon wafer, silver electrodes, copper ribbons and a junction box. The module buildup and the functionality of each material composing the module will be discussed next week. It is noteworthy that, at system level, more components are needed, such as inverters, transformers, a mounting frame, support structures and wiring. As the module technology evolves more rapidly and entails more options than the BOS structures do, separate life cycle analysis are typically performed for the modules and the other system components. Here we look at the share of materials by mass for a silicon PV module. Glass, polymers and aluminum dominates the mass share. Silver is not shown because it accounts for less than 1%. In the pie chart, the share for materials by monetary values shows a completely different picture. It is interesting to note that the monetary value of a PV value is mostly dominated by the metal consumptions. Silver's value corresponds to about 50% of the module's value. Besides mass and value, we also need to pay attention to the environmental aspects of PV. In the following, we shall discuss more about the environmental impact of silicon PV. Here we see the weighted environmental impact results of 1 kWh of DC electricity produced by a residential scale monocrystalline silicon PV system mounted on a slanted roof. The recycling benefits are excluded from the evaluation. The environmental impact is mainly driven by the mineral, fossil and renewable resource depletion potential, which is dominated by the silver consumption in the metallization procedure and accounts for 42% of the total impact. The other impact factors are mainly related to electricity production in the supply chain of the silicon wafer and aluminum. For instance, when burning fossil fuels such as hard coal, the resulting emissions of carbon dioxide causes climate change. Ultrafine dust and sulfur dioxides are emitted to the air, causing particulate matter formation potential. The sulfur dioxides, together with nitrogen oxides, are also the causes for acidification potential. The emission of arsenic and heavy metals such as zinc, lead, mercury cause non-cancer effects with respect to human toxicity. While the chromium emissions stem from disposal of hard coal, ash and red mud from bauxite digestions, processes for aluminum production are sources for cancer effects with respect to human toxicity. The freshwater ecotoxicity potential mainly occurs in the construction stage of PV panels. It's mainly caused by the antimony emitted into the water by the disposal of plastic components of the electric installation of municipal waste incineration plants. Besides heavy metal released in the supply chain of the wafer, and silver contributes to the freshwater ecotoxicity potential. Regarding the thin film PV technology, here we show a cross-section of a cadmium telluride PV module as produced by First Solar, a world-leading American manufacturer of this type of solar panels. Basically, a thin thin film PV module is composed of glass, polymers such as encapsulants, and cell material, which includes a transparent conductive oxide, an absorber material, a back contact, and metals, and so on and so on and so on. Of course, balance of system components need also to be considered, such as inverters, transformers, mounting, supports, and wiring. Different from silicon PV, in which the electricity demand for the production of high-quality wafers requires a lot of energy and induces various forms of environmental impact, a large portion of the energy consumption in thin film PV goes to the cell materials and balance of system components. However, the overall energy consumption of making a thin film PV module is less compared to the one of a silicon PV module. Previously, we talked about the cell structure of the commercially utilized thin film PV technologies, including thin film silicon, CIGS or CIS, and cadmium telluride, as shown here. This is a summary of the environmental impact of these three thin film PV technologies. The functional unit was defined as 1 kilowatt-hour of direct current electricity generation by a residential PV system. Recycling is excluded from the assessment. Notably, in the CIS or cadmium telluride cases, mineral, fossil and renewable source depletion potential accounts for the biggest share among the environmental indicators. They are mainly attributed to indium use in CIS and cadmium and telluride use in cadmium telluride technologies, respectively. Another remarkable indicator is the human toxicity related to cancer effects. It is mainly attributed to chromium emissions in the aluminum production and in the supply chain of aluminum and steel, such as red mud disposal from bauxite digestions and disposal of slag to residual material landfills. To recap, we spoke about the material use and consumption in mainstream photovoltaic technologies. Firstly, we discussed the case of crystalline silicon PV. The material mainly includes glass, polymers, aluminum, silicon, copper, and silver. Silver is only less than 1% of the total mass, but it is the material item that holds the highest monetary value. Moreover, silicon accounts for the dominating part in the mineral, fossil, and renewable resource depletion potential. The impact on the other environmental indicators is also introduced. In the second part, we spoke about the case of thin film PV. The utilized materials include glass, polymers, cell materials, and balance of system components. The latter two contribute the most to the environmental impact indicators. Due to the indium use in CIS and cadmium and telluride use in cadmium telluride technologies, high mineral, fossil, and renewable resource depletion potentials are observed. The large share of balance of system components for thin film PV should also be discussed, as they could possibly lead to toxicity and human cancers.